Hey everyone, welcome back to another video of Code at GWA. So today we're going to be going over Module 8. This will be the last module in the Fundamental series. We might go over Module 9 if we do a project that requires it, but for now we'll just be doing Module 8. So we'll be going over indexes and lists in this video. We'll go over how to index with iterables, and what the data type list is and the functions that pertain to it. So you can only index with data types that are iterables, and an iterable is essentially anything that can be sequenced through to return different segments of it. An index refers to a specific segment or element of an iterable. So for example, strings are a type of iterable, and if you call for the index of 2, then it will return the third element of it. So if you look here in this case, code at GWA brackets 2, these brackets notate that you want to find the second index of this string here, and this second index refers to the third element of the string here. It refers to the third one, not the second one, because elements start at index 0 when you go from left to right. So C would correspond to the index of 0, even though it's the first element. So here, code at GWA square bracket 2 and square bracket would return D because this is the third element here. Negative indexes work somewhat differently. It starts from right to left. It goes right to left, unlike left to right, with positive indexes, and the rightmost element refers to -1 rather than 0. So if you were to do code at GWA -3, it would return G because this is the third rightmost one. Indexes can also be used as ranges. So if you use an index colon index, then you'll be able to return every element within this range, excluding this index here. So it's from the starting index all the way to the maximum index, not including it. In this case here, since it's 3 to 5, it would return D, E, and at, because these are the third, fourth, and fifth elements. Here, if you don't include a starting index, then it will assume that you want to start at 0, so it would return code at, because this is the first element, second element, third element, and fourth element and fifth element. And the same works if you have no index at the end. It would return everything from the starting index until the end of the string or whatever iterable you have here. So the element that corresponds to the fifth index would be G, and it would go up to the end of the string. So in this case, it would just be GWA. And one thing to note with ranges and indexes, you can only iterate from left to right. So the position of the start of the index must be less than the position of the end of the index. So you can't have, for example, like 5 to 4 or 7 to 3, because the starting index would be greater than the ending index. Okay, so let's look at an example. So this code here pretty much returns a word backwards. We're defining two variables here. The first one is your input. The second one will be the output. There's a for loop here. The starting number, I guess, will be -1. The maximum or minimum in this case will be the length of the input -1, because it doesn't include the maximum or minimum number, so this way I have to do -1. And the step will be -1 for reasons you'll see later, or I guess now. We're starting at -1 because we want the rightmost letter of the input, and every time we iterate through this loop, we're going to be working our way towards the left of the string, because we'll be minusing 1 with every iteration of the loop, and it will keep on going until we've hit the length of the string. So it knows how long it needs to do this for. And then for each iteration of the loop, we'll be adding each letter to this to decipher the blank slate that we had before. And once the backward string is done, it prints the word. So let's say we want to type hello backwards. It also returns this. And if we want to make this go back to its actual word hello, then we would just do this. So in task 1, we're a member of an intel division, and we've intercepted an encrypted message. Our colleagues have found out that there are several rules that we can use to decrypt this message, and they've applied these to decrypt the message we intercepted. So the first rule is that the third character of every encrypted message will always be the first character of the decrypted message. So see here, the third character of the encrypted one is R, and that tells us that the first character here is R. Next, we know that the remaining characters of the decrypted message will always start at the same position in the encrypted messages. So for example, the remaining letters here, they could start in position 3, like index 3 here, or index 5 here. They could start anywhere. But we know that the remaining ones will always be bundled together and always start in the same position every time, in every encrypted message. Lastly, we know that the last character will always be a number, and this will refer to the length of the decrypted message. So 7 here tells us that the decrypted message of this encrypted message is 7. So knowing all this, we need to make a code that can decrypt encrypted messages. These rules will always be the same for every encrypted message. So make a function knowing what you know now, and test them out using custom inputs that follow the same encryption rules. So this is my code here. I've initialized the encoded message here, initialized the decrypted message here. We always know that the third character, or the third element of the encrypted message, is always the first character of the decrypted one, so this is why I've done this. The for loop here is made in a way so that it always starts on the 7th index or 8th element of the encrypted message, because you might have noticed the remaining characters started on the 8th element. And using the rule that the other decoders have found, we always know that the remaining characters will always start on the 8th element. So this is why I've done 7 here. Since we've already used one of the characters, the remaining characters that we need to get equals 6. Because we know this is 7 characters long, we've already used one, hence why there's 6 left. This is why I've started with 6 here. Remember, this is the maximum value. So using this, what I've done here, we would get, this here would equal 7. What I've done here is I've gotten the last letter of the last character, of the encrypted message, and made it an integer, because this is a string, so I need to make it into an integer. And I've added it to 6, not 7, because 6 plus 7 equals 13, and there are 6 remaining characters, not 7. So we just need to pretty much minus 1 to this, because we've already used 1 here. Another way you could do this is just do -1. This also works. I just did it the long way for some reason. This would be 17. The way this works out, in this case, would be 13. That works out because it's 7, 8, 9, 10, 11, 12. Those are all the characters remaining that we need. And using these values, we can pretty much iterate through the remaining characters in this encrypted message and add it onto the decrypted message, concatenate it. So once all of that has been finished, we'll then print the decrypted message, and that's the end of the function of the code. So let's use the example here. As you see here, we get the right message, and let's say we've got another, we've intercepted another message. Remember, it uses the same rules as these. And you see here, it also decrypts it properly. So hopefully you guys have managed to do that. If it doesn't make sense, please email Suraj and I. I know this is kind of complicated, but yeah, it's certainly doable.
Okay, so we're going to talk about lists, which is a new data type. Okay, so to start with, we declare lists using this bracket syntax right here. So we can see that we have brackets at either end, and within those we have our regular strings and ints. So here we can see that this string has a 3, which is an integer as its first element, a 4, which is encoded as a character or a string for its second index, and a 5.0, which is actually a float in its third index. So here, much like strings, these are iterable, meaning that we can refer to a specific index on them. So here we can see that if we have the same list that we defined up here, the second index would be, if we put 2 as an index, it would return 5.0. And this, again, if you remember, is because lists start at index 0. So this 3 would be at index 0. So if we were to put 0 here, it would return a 3. This would be a 1. This would be a 2. So because of that. Additionally, if you put -1 right here, it'll return the first 2 right here. So it'll be 3 and 4. Now, since we can refer to these elements like this, much like any other variable, we can change its value. So here we can see that we have the exact same list that we've been using for the past examples. Second index, so that would be 5.0 right here. And when you actually make this statement, you pretty much treat this entire statement as a float, which is 5.0, or not really as a float, but pretty much that little space in the list. So much like any other variable reassignment, we just put the equal to sign and a new value. This is actually also in a new data type, but don't let that confuse you. So here, when you do make that variable reassignment, you'll get a list much like this. And the list would look like this. This 2 is there just for convenience, because it's again just to show you that we are referring to this index right here. Similarly, like strings, we can use len and in, much like strings, because they are iterable, again like strings. Now with these lists, we get access to a whole bunch of higher order Python methods, and there are more. You can search them up, but these are a very, very good set to start with. So first one is quite easy. Append. It pretty much places whatever you pass into the function, whatever is the parameter, into that list as its very last element. So for example, if we had this list and we did dot append and we put a 1, you would pretty much get 3, 4, 5, and then a 1 at the end. This is very useful. You can see this used lots. Insert is used to, as the name suggests, insert a specific element. However, unlike append, you can specify the location or the index where you want it to be inserted. So this, like the description says, it accepts 2 parameters, first of which is an index, and the second of which is a data type to be put into the list. So dot remove is again pretty self-explanatory. Whatever you pass into the function, if that exists in the list, it will be removed. If it's not in the list, you'll get an error. Dot pop. So pretty much for dot pop, you input an index, and that will be removed from the target list. This is different from dot remove because with pop, you pretty much specify an index, whereas with dot remove, you specify the full data that's being held in a specific location. Sometimes dot remove is easier, sometimes dot pop is easier. You'll again see examples of this as we move on. Dot clear is quite uncommon, but it's still used. Pretty much all the elements will be removed from the list that you run it on. And one thing I do want to mention, if you guys have forgotten, much like the string higher order methods, you put the string dot this. So you put string dot this function. Don't make the mistake of declaring this function and passing it in here. That's not how it works. Okay, all right, yeah, del again is pretty self-explanatory. So some other relevant functions we have is count, and this returns pretty much the number of inputs that are in the specified list. Dot index returns the first index in the input, so it pretty much runs a search algorithm and returns the index, whether that be 0, 1, 2, 3, or n, of wherever that data type you pass into it appears first on the list. Dot reverse, much like we have for string, it reverses the order of the list. So this would become 5, 4, 3. Dot sort, when we have a list dot sort, and then we call this method, it alphabetically sorts it. However, you do have a whole bunch of inputs, and by inputs we mean parameters that you can pass into the function, which can be found on the Python documentation to change the sorting behavior if you want it to go from Z through A, or if you want to do some other things. Okay, so this brings us to the example of this. So this, it does look a bit complicated, however, don't let that get into your head. So this is actually, it's kind of taken from an anime. Actually, Jacob is quite fond of this, so you're going to see a lot of references like this. Okay, pretty much, we're storing a whole bunch of values inside this list, and actually you can see this is quite a high level way of declaring 3 variables. We're pretty much declaring 3 at a stretch here, and then we do equals, and we use that same order. So incomplete will be assigned true, BB will be assigned this massive list that we see of names, and other target will be this input that actually appeared here. Okay, let's run this again. So this is again the yes or no prompt. For example, let's if you want to add something to the list, we can put Y, and this resolves to this next part right here. And you can see that whatever I type into here, let's say hello, that actually gets appended to the list, meaning that it'll get added to the very last element of the list. So here, yeah, it says, all right, noted. And then here, you know, it again asks who can be eliminated. Let's pick one of the names here. Let's do this person right here. And as you can see, when I do that, what happens is it pops the element at this index. Here we can also use the remove method. However, just to show you two methods used in conjunction, we're using pop in combination with index. If you see, index refers to the index actually where this dead variable is. So when we pass in this name, it does a search algorithm and returns an index of 1. And then that value 1 is being passed to the bb.pop function, which pretty much pops or deletes the value with an index of 1, which happens to be this Itachi. Now here, after this code is run, we can actually see the end product of both of our actions that we did up here. We can firstly see that hello has been appended to the list or added to the very end, and that, as I previously explained, this name has been removed from the list.
So now let's go over 2D lists. So far we've only covered 1D lists, meaning we've only had lists that contain anything that's like not a container. A container being something that can contain multiple data types like a list. In this example here, you can see that this list has a list in its first element, a string as its second element, and a float as its third element. And if we were to call the 0th index, or the first element, of this list, then it would return the list itself. When it does this, we can add another square brackets after this one to call the second element of this first list. So this 0 here is calling the first list, the first element of this list here, so this one. And once it's called that, we're calling the second element of this list. Okay, so let's go over an example. So here we have a list of fruits and vegetables. Well, I should say a list of lists of fruits and vegetables. The overall list we'll call the global list, and the list within that overall list, the global list, will be called nested lists. The first nested list corresponds to fruits, the second corresponds to vegetables. Here we're just printing out this list to show us what it's like. By doing this, by having this statement here, we're essentially calling the first list, the first nested list within the global list, because this corresponds to the first item or first element within the global list. Because this would return the first item, it's returning a list, meaning we can apply any function that pertains to lists. As you already know, .append is a function that can be used to add any item to a list, and since we're returning a list, we can use this on this statement here. Same logic applies here. By doing fruits and vegetables index 1, we're calling the first index or second element of the global list, which happens to be the vegetables list. And then, since it's being treated as a list, we can then do index of 2 to get the second index or third element of this list, since we've just called it using fruits and vegetables index 1. And by doing this, we can assign a new value to the second index or third element of this list here, the vegetables list. So this would turn beans, because this is the third element of the vegetables list, into green beans. And we can see both these changes, the addition of banana and the change into green beans, with the terminal here. So you can see this was the original list. We add banana to the fruit list by doing this, and we changed beans to green beans in this list.
Moving right into task 1.2, we can see that we're given this large, I guess, string of grouped characters, and like the instructions say, we pretty much have to not only decrypt each string, like each element within this, using our previous decryptor function. We also have to do some manipulations with the integers that we find in this. Okay, so moving into the code, first all I've done is I've pretty much packaged our code segment from task 1.1 into a function. But instead of asking the input for a user right here, I've pretty much turned this into a parameter that the function accepts. And instead of returning the decrypted string to the console using a print statement, we're returning it as a result of the decrypt function. Okay, so first within here, I'm pretty much taking this stuff that we see up here and putting it in list form. Thankfully, we have put these already in quotation marks and commas, so all you have to do is copy paste that and put the square brackets on either side. Like we've previously talked about in the module, this is the correct notation for a list, which is the square bracket on either side and data types in their respective forms with commas to separate them. And then I've created 4 additional empty lists with names and purposes, which I'll explain next. So we can see that it first asks to only decrypt the words which do have an integer at the end. So in order to filter those, we pretty much I don't know why it keeps doing that. We pretty much just loop over the list and we look at each element. And what this notation pretty much says is that for each iteration, it sets a certain element which is assigned to raw message. Sorry about that. Which is assigned to raw message, and that can be referenced within our for loop like we have done before. So we have to pretty much test if the last character of the raw message string, which is each individual string, is a number, and for that we can use the .isNumeric function combined with the location. So it'll be raw message, and our index will be -1 because we're looking at the last character, and in Python an index of -1 immediately jumps to the last character. So if this statement resolves to true, we're going to be appending this list. As we discussed previously, append pretty much adds the argument of the function to the end of the specified list, which is MSG list filtered. So pretty much if it ends in a number, we're adding that into our filtered list. If that does not happen, in order to satisfy the next thing that the task calls for, which is filtering the II numbers, or the II messages, which are pretty much each individual messages without a number at the end. So in order to do that, if this statement resolves false, which if there's no number, this will resolve true because it's an else statement. And if that resolves true, we'll be appending, the raw message, but to a different array. Instead of MSG list filtered, we'll be doing it to MSG II. So this is our initial filtration process. And then we pretty much just print out this filtered list right here, this one that we append a whole bunch of elements to. And this is just for our sake, the task does not call for this. And then, and when we do run that, our filtered list will pretty much be this. It's not decrypted yet, it's pretty much just filtered to the ones which we need to decrypt. And to decrypt this, it's pretty easy. We again iterate over each element within the filtered list array. And we're going to be appending the decrypted message, so by message we mean each individual one here, to the MSG decrypted one list. And here we're pretty much like nesting the functions. I'm sure you guys must have seen this from our nested module, from our nested functions module. And then after that, we're just printing out the full decrypted list, which you can see right here. And here we can actually see that it makes sense. So it says retreat back and convene with the third division. Now, in order to do the next thing, which is pretty much filter out the numbers from the individual messages which did not contain integers at the end, we have to do some further processing here. So over here, we appended the raw messages to our II list. And from this II list, we have to pretty much extrapolate 2 numbers. And those 2 numbers are located at the 2nd index and the 7th index. Now, if the length is larger than 5 characters, the 7th digit also exists, the 7th character also exists. If not, it's just the second index. So in order to run that check, I pretty much do an if statement to check if the length is greater than 5. If this is correct, it pretty much appends a list containing the second character and the 7th character like so. If that's false, so for example, for this one right here, this is shorter than 5, it only appends the second character, which is 7. And here you can see that I'm using an extra bracket, and that's because we're in fact creating a nested list. And this again is because the directions call for it, and it's going to get a lot interesting further down. So for now, that's why this is like that. And again, much like this, we're printing our finished list with an appropriate heading. And as you can see, it works. So this is what I mean by a nested list. As you can see, it's pretty much a list within a list. So at the first index, instead of having just an integer or string, we have another list, and inside those lists are the individual numbers.
So let's do task 1.3 now. This one's a little more simple than the last task, but it just progresses on the scenario that was established before. So other members of the Intel division have reported that certain parts of the intercepted message were transmitted differently to other opposing officers. It seems that the 4th element in the series, which refers to convene, could have been this, this, or this, and the 5th element, which refers to with, could have been this or this. So now change convene and with so it reflects the possible messages that it could have been, and do this by inserting lists in place of these. So for example, once you've decoded what all of these could be, add them into a list, and then add that as a nested list within this global list to replace convene, and do the same to replace with. Okay, hopefully that wasn't too difficult. It's just mostly recycling code from the last tasks. What I've done here is I've made 2 empty lists to store the first alternatives and the second alternatives. So the first alternatives to the 4th element and the second alternatives to the 5th element. I use 3rd and 4th here because I'm referring to the index, not the element. Now I've used a for loop to pretty much decode or decrypt all of these messages here, and I've used the function that was used previously in task 1.2 to do so. And then I've just added those decrypted messages to the alt third, the list that corresponds to the 3rd index. And then I did the same for alt 4th, the alternate 4th index. And then once I did that, I pretty much changed convene and with into these possible outcomes. So as you see here, the original list was retreat, back, and convene with 3rd division. But now I've converted convene into these possible words, and with into these possible words. So now the sentence can have multiple interpretations if you consider these new words.
Okay, alright, so jumping into task 4. So this is pretty much where all the 1.x tasks kind of culminate. So just sort of unpacking this, we see that we have been given 3 new messages, and these are in the similar encrypted format where we have a mixture of elements with the elements ending in an integer and not ending in an integer. And as we saw in 1.2, the ones that do end with an integer will be filtered out, and our decryption algorithm will be run on each element. And the ones that do not end in an integer will be the ones where we can pretty much extract a hidden number from. Now in this task, the use of that hidden number is seen. So pretty much going through the code, first we again create a function using something in the previous task. So this is pretty much the main logic from task 1.2 that's pretty much neatly packed into a function. So the function takes an input list. So this is a list full of those encrypted messages, so pretty much this whole thing. It filters that list, like I said. It pretty much takes out the ones that end with numbers and put that in a separate list, and takes the ones that do not end in a number and puts that in a different list. So we have message list filtered and message II. And then out of the ones which it has filtered, it runs the decryption algorithm over, and the ones that it has pretty much left behind, it figures out the missing numbers. Now, we return both those things kind of uniquely. So we do return message decrypted 1, which is our variable that contains the decrypted words. So this is just the words. And we have our II nums, which is pretty much a list of the numbers extracted in their correct order. Now, having a function return something like this, it will return a list. So usually when you do return in a single variable, you either get a number or string. But in this, we pretty much have a list. So in order to process these outputs, we'll have to use the list index notation, as you'll see further below. So first we'll just run this, and that's just to load this function into memory. Since it's purely a function, absolutely nothing will be executed for us to see. Okay, then we pretty much grab our message D1, which is just, you know, like a decrypted one. That's why I've called it that. And this is pretty much from the task 1.3 output. So you can just go there and grab that. And then these are the 3 new messages that we get. These are pretty much just copy pasted from here. Here we can see that here you can see that we have put the square brackets already. So you literally have to copy paste that and equal that to a certain variable name. Okay, so now this is where the interesting thing happens. We already have a decrypted list right here, which is message D1, which we decrypted in task 1.3, and it has lists nested within that, right? So as we previously said, this section right there can be one of 3 words. It can be convene, break, or ambush. Same thing with the next word. Now we want to preserve this structure and still add on. So we pretty much have this, and we do an append method like we discussed previously. It pretty much inserts an element in the very last index. We append the decrypted version of these. So for example, our first append method will be this array dot append, and we'll be using our decrypt list function and passing in this. Now when we run decrypt list, it'll pretty much like I said, filter those, and we'll get a message in this list, and we'll get the numbers returned. Now that will be a list. So we have to again, use the index notation here in order to just get the message decrypted 1 list, which is purely the words and not the numbers. And as you can see, we do the same thing for raw message 3 and 4. So let's run this and see what our new message D1 looks like. So before, it started out just simple like this, but then with each line we have more things being appended to it, and it becomes a nested list or a multi-dimensional list. So what this pretty much reads is, okay, it's in a little bit of a different format. That's because we're just putting the variable name at the very end. So we're letting Jupyter print it, or Jupyter or Colab print it automatically to the console. Now this gives us a little different format. I'm using this just to show you that there are 2 methods, and just so that you feel comfortable with both formats being used. So we can, just reading this out, we can see that the message is quite long, right? So it has these words, but every time a list is nested within, it can pretty much be one of those elements right here. Now, in order to determine which one of those elements are needed and are important, we use the mystery numbers that we have got previously, which is our II nums array. Now, in order to do that, we pretty much take these raw messages, put them through our special function, and refer to the second output, which is our II nums, which we do square brackets 1, because as you know, arrays or lists begin at 0. Now here I'm just putting raw message 1 again. This is straight up from task. This is straight from task 1.2. The reason I'm copy pasting this again here is because I can't use this one because it's already, like, the word's already there and the raw message isn't. So I pretty much declared this again, and since raw message 2 through 4 are already declared up here, we can simply run this to get our final IIs. Now here you can see another list method being used. This is simple concatenation, as we've previously shown, where pretty much the II nums are taken from the first message, second message, third message, and fourth message, and they're simply concatenated together, much like string concatenation. Now let's print our final II here. We can see that it is a whole bunch of numbers that refers to a variety of things. So using this, using the next piece of code right here, we can pretty much, because these are pretty much the indexes to look for in this long message, which will neatly show us the end message. So, I mean, like I said, there's a lot of information here that's not useful, and this is pretty much what finally unlocks the full message. Now, what this code does is it pretty much iterates through this list, and for every number that it sees, it pretty much, at that index, it looks at the long list and figures out what word falls in that index and appends that to our final message list right here. And then, in order to convert our final message list into a string, we use the .join method. There are a variety of ways to do this. We just use the .join method because it's the simplest. However, you can, do a for loop where you automatically append a space as you concatenate each element to a string, and then equate that to final message, as we can see. And then we're just printing that. So let's run this, and there we go. That is our final message. Convene with the 8th division fast. The Eastern Front will break. So if you could do this by yourself, pat yourself on the back. This was extremely well, okay, not extremely, but much more difficult than what we had before. And actually, a lot of the difficulty actually came from pretty much breaking the problem down. So that's why the video is a lot more, or is more helpful for this one than the previous ones. Yeah.
There was no real spot to put this in before, but if you ever need to copy a list, then use the .copy function. Don't assign a variable to it and then assign another variable to that, because ultimately, if you change a list and a variable is assigned to it, or multiple variables are assigned to it, then every variable will change. So if you want to make a separate copy of a list, then you have to use .copy. Okay, so this is the final task of the module. This is going to be quite a big task. It might take you multiple days, and that's perfectly understandable. It is fairly difficult to code at the current level you're at, but this will be a nice way to wrap up the fundamental series, and this will be a good transition into the project series. So let's get into it. So we're going to be making Blackjack, and if you don't know, Blackjack is a card game where your objective is to get more points than your opponent without going over 21. So the maximum score you can get is 21. It uses a standard deck of 52 playing cards, and each card has a specific number of points. So cards with a number on them, so like 2s, 3s, 4s, so on, are worth the number that they have. Aces can be either 1s or 11s. You decide what the value is. Kings, queens, and jacks are always worth 10. You automatically win if you have 5 or more cards and you aren't bust. Bust just means you're over 21, and your opponent will be a computer, so it won't be a program designed for multiplayer, but you could make it like that if you want. You won't be able to see the computer's cards until you decide to stop drawing for that round, or you are bust. And you always start with 2 cards, and you can continue to draw more one at a time. And if you're over 21, you automatically lose. So let's go over everything that you need to include in the code. Firstly, you need to start with 2 random cards and remove them from the possible cards that can be drawn. Now, like in any card game, you have a deck, right? And every time you draw from the deck, a card will be removed from the deck. So you should make a global list with all the possible cards in a playing card deck and remove it every time you draw one. If you don't know the possible cards, by the way, then check here. These are the possible cards that can be in one suit, and there's 4 suits, so just multiply all of these by 4 and you get a total deck. The value of your hand should be displayed every time you draw a card and after your 2 starting cards have been chosen. Next, you should have an input message that asks you if you want to draw another card. If yes, then you should add that card's value to your score and remove it from the possible card list. and your updated card value should be displayed after that. If no, then your turn ends and the computer should be drawing its cards after that. There obviously has to be logic for the computer in the way in which it draws its cards. You can do it in multiple ways. If it's below 21 cards, 21 points, sorry, you can make so the computer always draws. This will make the game quite easy because if they're on 20 points, then it's not smart for them to draw. Alternatively, if they're below a certain threshold, then a randomizer could be used to determine if a card is drawn or not. So like if you're below 15, you can make it so that there's a 50% chance of drawing another card, and so on. A similar idea could be used in another method, where the likelihood of a computer drawing a card scales with the current value of its hand. So for example, a hand of 10 means that the computer would have a 100% chance of drawing a card, because there's no risk of going over 21. But a hand of 16 carries a lot more risk, so the chance might be lower, might be 40%, and a hand of 18 might have a 20% chance, and so on. If you know how to do expected value and probabilities, feel free to use that as well. I mean, that's the way I've done it, as I'll show you later. But just feel free to just tinker around with the logic and do whatever you feel most comfortable with and best reflects a computer. Additionally, you should also have checks to see if you or the computer goes over 21, or if you or the computer have a hand of 5. If any of these happen, then obviously it's an automatic win or loss depending on what the outcome is. Your values and the computer's values should be compared at the end of the round, so after the computer has stopped drawing, to determine a winner. Note that the computer always wins if there's a tie. You should also have the option to choose whether an ace is equal to 1 or 11. This might seem a bit daunting at first, but before you start coding anything for this, just think about the logic behind this, and it will become a lot easier once you realize there's certain caveats that apply to this feature, so just note that. You should also have a feature that shows your current cards. Just so, I mean, you don't have to, but it's just obviously nice to see what you have. And these are some optional things that you can do. You can add an option for the player to play again with everything being reset, so they don't have to keep on running the program every time they want to play again. Alternatively, you could have a scoreboard to see how many times you've won or lost. Or you could have like a betting feature where you have a pool of money that you have. And you and the computer always have to bet a certain amount every round, and whoever loses all the money first, loses. So just to recap the rules of Blackjack, you start with 2 cards and you can decide to draw one at a time. You automatically win if you hold 5 cards, but you automatically lose if you're above 21 points. The computer goes after you and you can't see their cards until you've settled. And if you have a tie with the computer, then the computer wins. Pretty much number cards are worth a number. Aces can be either 1s or 11s. Kings, queens, and jacks are all with 10. The possible cards in a suit is the following. Note there's 4 suits, so it's this times 4. And yeah, knowing this, go ahead and code. Sorry, one more thing I forgot to mention. One more thing I didn't mention. You have to use the random library in this to add the random functions in. Just do import random, then do random.seed to initialize a random seed. Don't worry about what this means, it doesn't really matter right now. And then the function that you need is random.randrange, and this will generate a number within this range randomly. So this is the starting position, 1, and this is the ending position, 3. So it can generate a number between 1 or 2, because the ending position is not counted. Note that if you have nothing at the start, then this is just the maximum value. And if you have a number at the end, this is a step value, meaning in this case here, the numbers could be 1, 3, 5, and that's it, because the step value is 2. Yep, so knowing all that, go ahead. Good luck. So this is my code. Your code might be shorter than mine. This could definitely be shorter, but it is what it is. So here I've initialized a global variable continue. I've just named it CONT for short, and this is a boolean, and I'll show you what it does later on. Here I've made a function called ex. This is an expected value function, and this pretty much returns what the expected value of something is depending on the input. So in this case, it returns the expected value of the next draw, depending on what the current state of the deck is. And this is what the computer will use to dictate its actions. So when you're playing against the computer, you'll be fighting against quite a formidable opponent. The code of this function doesn't really matter because unless you know what expected value is in maths, then you wouldn't really understand what's going on here. But if you do know it, or you just want to know about it, then email Suraj and I, and we can tell you what it is, and I can explain this code here. But for now, you don't have to worry about this. So here, the main body of my code is within a while true loop. This means that the game will continue to run until I specifically tell it to stop running. So this will allow us to keep on resetting without having to restart the code. So the only way to get out of this loop is if we tell it to break manually. Okay, so just note that there's multiple ways to make this code. So you could have done it in a different way, and it might be perfectly valid. So what I'm presenting now is just the way I would do it. And this is a good introduction to the project series because it will be like that. The videos we'll make for that won't be indicative of the only answer. You can always make a different code that pretty much has the same function. Here I've initialized a deck of cards in this list. Here I've initialized something called p-cards. This variable shows what cards the player has at every point in the game. Here I've initialized p-score and c-score. This is your player score and computer score respectively. And here I've initialized something called ace value. And this variable is quite important, which I'll show you why later on. So once we've initialized these variables here, we get into the player phase. So this player phase is stuck in a while true loop as well. And the reason for that is that for loops, you don't know how many times you want to loop a full loop for in a player phase, because you might want to draw a card once or 3 times, or you don't want to draw a card at all. So the amount of times you want this to loop is unknown, hence why I used while true. Random.range was used here to generate an integer that corresponds to a possible index in the current deck of cards. At the start, the deck of cards will be 52 elements long, but obviously as the game progresses, as you draw more cards, this list will start to deplete, and this length cards function will reflect that. So this will return the length of cards. This will generate a random number within that to simulate the randomness of drawing a card, and this number will correspond to a possible index in here, and draw will be equated to one of these cards in the possible deck. So now that you've drawn a card, you have to check at what card it is and how many points to add correspondingly. If it's an ace card, then it will do the following. I'll explain why I did this later. If it's an integer, meaning if it's one of the number cards, then it just adds the number onto your total score, because that makes sense, right? And then finally, if it's none of these, then it has to be a face card, meaning a king, queen, or jack. And all of those are worth 10 points, hence why I did plus equals 10. Next, I did p cards plus equals a string of draw. This is just to display the current hand you have. So once you've drawn a card, it calculates the score you have, and then it just adds that to your hand. I did string draw because obviously if you get one of these numbers, these are integers, not strings, and p cards is a string. I've initialized it to be so. So it can only add strings to it, hence why I did this. Next I did cards.remove draw, because obviously once you've drawn that card, it can't be in the possible deck, so you have to remove it, hence why I did that. Since you have to start with 2 cards before you start drawing, I added this if statement here to reflect that. So if the deck of cards is less than or equal to 50, that means you've already drawn 2 cards, which allows you to start drawing. But if that's not the case, then it moves on to this statement here. And this is p cards plus equals comma space. This pretty much adds a comma and a space between each of your cards within your hand in the p card string. And this is obviously just to make it more, just to make it easier to read. And the reason why I didn't add it here is because it messes up with formatting later on. So it's just easier to put it here. Let's say you've drawn 2 cards already. It then allows you to go into this loop. It will firstly show what cards you have by printing your cards are and then displaying the string p cards. So here is your last condition. It checks if your score is over 21 and if the ace value is equal to 1 or nothing. I'll explain what this means later on. So if you're over, and this is the case, then it will tell you you're bust. It will make the continue boolean false, and it will break out of this while loop to end your turn. And this continue value is used to see if you want to go to the continue to the computer's turn. Obviously, you don't want to do the computer's turn if you've lost. So this is why I've added this condition here. So it skips all of this to go straight into the if statement asking if you want to play again. And obviously, if you don't want to play again, then it'll break out of the global while loop and the program will end. Next, it checks if you have 5 cards. This is a win condition, not a loss condition. If you have 5 cards, then you've automatically won. So that's why this is a specific condition. There's nothing really else to it. If the length of the deck is 47, that means you've drawn 5 cards, because 52 minus 5 is 47, obviously. So when this condition is met, it'll print this. It'll also make continue false, and it'll break out of the loop and repeat the same thing as before, but this time you've won instead of lost. In these cases, if you want to add a betting or loss, like a win or loss tally, then you would obviously add some functions here to reflect that. Okay, so if you haven't lost and you haven't won, then that means you can still draw cards. And this is where I explain the ace value. So I told you guys before that if you logic your way through about the scenario of choosing an ace to be 1 or 11, then you'll notice that only one ace can be 11. Even if you have 2 aces, only one of them can be 11, because if they're both 11, then that means they're 22, which is over 21. So I used ace value to reflect this. The ace value tells us whether or not one of your aces is 1 or 11, or if you have any aces at all. If the ace value is blank, that means you have no aces. However, if it's 1, then that means one of your aces is 1. If it's 11, that means one of your aces is 11. You don't need to take into consideration the value of your other aces, because they always have to be 1. Only one of them can be 1 or 11. So this condition here checks if you have an ace value of 11, and if your score is over 21. This pretty much checks to see if you have a score that's over 21, but you have an ace value of 11. Meaning, like let's say you have a 10, a 5, and an ace, and you've made this ace to be 11. Obviously, this will be 26, which is over 21, but this ace can be 1 as well. So this condition here forces your ace to be back to equal 1 again. It essentially minuses 10 and makes your ace value 1. I've done minus 10 here because up here I've made that so every time you draw an ace, it always adds 1 to your score. Because no matter what, an ace will always equal at least 1. This is why I did that. And this just reflects, if it's 11, then just minus 10 to make it 1 again. If this is not the case, then this is the condition to allow you to choose what value your ace takes. You can only change your ace to be 11 if these conditions are met. Firstly, your score plus 10 needs to be less than or equal to 21. Obviously, if it's greater than 21, then your ace can't equal 11, and an ace has to be in your hand. It firstly asks for this input. You have an ace. Would you like it to be worth 1 or 11? You either respond with 1 or 11. Depending on your outputs, it calculates your new score. So this calculates your new score. Pretty much what's happening here is that I've made the ace value an integer rather than a string, because remember that the outputs of inputs are always strings. So I've converted this into an integer, divided by 11. If it's 1 divided by 11, it'll obviously be a decimal. But since when you apply an integer function to a fraction, if it's always less than 1, it'll always round down to 0. Hence, if it's 1, this will equal 0, and your score will plus equal 0, which is fine because you've already added 1 to account for that ace already. So nothing changes there. However, if you've wanted your ace to be 11, then the ace value will equal 11. 11 over 11 is 1. The integer of 1 is just 1, so 10 times 1 is 10. So your score will be plus equals 10, and 1 plus 10 equals 11. So now your ace equals 11. This is quite complicated. I just didn't want to write more lines than I had to, so I felt like this is the best way to do it. If you didn't do it like this, you'd probably have to use an if statement to consider your possible ace values. And then you just have the statement here to show you that your ace value has been updated. Remember that your ace value only applies to one of your aces because you can't have more than one ace that's worth 11 points. Coming back to this condition here, the ace value equals 1 or nothing. Remember that if your score is over 21, it doesn't necessarily mean that you bust, because in the example I gave before, let's say you have 10, 5, and ace, and that ace is equal to 11, then obviously is 26, but it can also equal 16. So you're not bust yet. You're only bust if your ace is equal to 1, or if you have no aces at all. And that's why I added this condition. So finally, we come to the option to draw more cards. It's just a simple input function. The only response that we'll recognize is n, because if you press yes, then obviously nothing needs to happen. You can just keep on looping in your player turn until one of these conditions happen. But obviously if you press no, then you want to break out of your player phase and move on to the computer phase. So that's why this is the only condition that I recognized here. So if you do press N and you want to exit your turn, then it will tell you that your turn is being ended, and it breaks out of the player loop and moves on to the computer loop. So the computer turn is pretty much the same as the player turn, minus a few differences. I've added this here just to tell the player that the computer is still taking its time. Again, I've got the same draw equals random.range function here, but I've also reinitialized ace value to reset it, because obviously you don't want your ace values to carry over to the computer. The same logic here, same logic here, same logic here. It removes cards like it did in the player phase. Difference here, instead of checking if you have if it's less than or equal to 50 cards to see if you have 2 cards in your hand already, it does this 51 minus p cards.count, comma. This pretty much checks how many cards you have and subtracts it from the total amount of cards that can be in the deck. So obviously if you've drawn, let's say, 2 cards, there'll only be 1 comma. So 51 minus 1 is 50, and that's how many cards are left in the deck. And that obviously is a generalization of the possible outcomes that could be. Then you have the same lose condition for the computer here, with the ace values and everything. So here we pretty much have the same thing that we had in the player phase, where it checked if the player had 5 cards, but in this case it's the computer checking if it has 5 cards. And it uses the same logic that we used up here, except it uses 46, because now we're checking if the computer has 5 cards. And mathematically speaking, this will always work out to see if the computer has 5 cards, just based off the amount of cards the player has. So if the computer has 5 cards, they automatically win. The message tells you that. It breaks out of the computer phase, and it goes straight to the would you like to continue playing if statement. But if the computer has neither lost or won, then it goes into the selection stage like the play phase. So again, it has the if ace value equals 11 and p score is greater than 21. I explained that before. Again, same thing here. But one thing I didn't mention is that the computer will always make the aces 11, and they'll only change it back to 1, obviously, if it's over 21. So here, this is what the computer uses to decide if it's going to draw another card. C-score plus E cards. So the E thing is what I explained before to be the expected value. So this logic here is saying if the computer score plus the expected value of the card is greater than 21, then it won't draw another card. Because obviously it wouldn't if it's expecting a value greater than 21. If it does, if this condition is met, then it will move on to the final stage of the game where your score is checked with the computer score. So here this is printing your score and the computer score. Then if the computer score is greater than your score, then obviously they have 4 points on you and they win, vice versa. And else, if the computer score is equal to your score, they win because it's a tie. Yeah, so this is the condition required to break out of the computer phase. This is technically still within the computer phase. And obviously if it still wanted to keep on drawing cards, then it just won't meet this condition. And it will just keep on drawing more cards until it has met that condition. Because eventually it will. So yeah, that's pretty much it. I've already explained what this does. If you have any questions on specific parts of this, then please let me know. I know it's quite long, and it's fairly complex for fundamentals task. But you can do all of this with the skills and knowledge you have now. So let's run it and just do some trial games. So 4 and 6, I have 10 points. Yes, I want to draw another card. I now have 4, 6, and 2. I think it's worth it. I have 20 points. I'm going to stay. Let's calculate the computer's turn. I've won. Nice. Let's do another game. Ace and Jack. Of course, I'm going to make it 11 and 21. So unless the computer gets it 21, I've won. Oh, yeah, they've won if they have 5 cards. Uh, of course. I'm gonna risk it. 16's quite low. Oh, nice. Yeah, I'm not gonna do another one. And there, I've won again. Let's do one more game. I've tied. You see the fun. Um, so yeah, that's Blackjack. Uh, when you finish your code and you're running it, just make sure you've gone through each condition, each possible condition. So see if your bus code works, if you've gotten 5 cards, so you've automatically won code works. Just check if every win condition and every loss condition is functional and working. And once you've done that, your thing is done. So that marks the end of Module 8 and the Fundamental series. Hopefully this was a fairly engaging module. I know it's quite complex and difficult. The encryption code thing I made to be quite complex. So you have something that's more engaging than usual, and something that's more akin to what you might actually do in real life. Right? You're not going to get some straightforward thing that you need to code. You're going to have to work out how to do something, and go through the process of deciphering things and just using reasoning to decide how to code something. Because I'm sure you found the code was pretty easy to make. It was just figuring out what to do was the hard part, and that is one of the hardest parts of coding. But yeah, hopefully you guys have had fun with this one. We'll see you in the project series, and thanks for watching.